this event and about neuroscience in the school. We'll spend 3 minutes on this. And next, Boris will introduce our guest speakers, yeah, and we will move on with Kingston presentation. Okay, that's the plan. So we say a few general words about neuroscience at this university because it's still a new topic here, and 3 minutes for this, 2 minutes to introduce briefly our speakers, and we move on. So we're now online. So we now broadcasted in YouTube as well. I see it.
Василий, у вас что-то со связью. Так.
Раз. Можно меня слышно? Can you hear me? Okay. Victoria, can you monitor questions in YouTube? I will also do it. But when I started, it also
пошлю.
No problems. I will. It means I will monitor. I will monitor. Okay. So we start in a minute.
Василий, могу в WhatsApp посылать.
Ладно, я буду этим заниматься. Приглашаю перейти на английский. So I will share my few slides, okay?
А можно я тогда начну и сначала сделаю заставку, чтобы мы после этого круглого стола после этого могли уже начать, да, и трансляцию начать. Хорошо?
Конечно, да.
Смотрите, вот тут какая-то накладка с чатом. So we have some. It's not a problem. I think we are all learning a new program. We have a small problem with chat, so it's not working for the moment. So for to do this round table live, I will ask you, the organizer, maybe to give the right to speak to the persons who will hand up hands. Maybe it will be a decision.
Who can do it? Who can give these rights?
Хорошо, тогда вот так
кто
сделаем.
Может дать эти права?
Это у нас наш инженер Александр Карпинский. Я тогда буду его просить давать права, чтобы можно было задать вопрос тем, кто будет поднимать руку.
Отлично, я это еще расскажу. Договорились.
Да, вот сейчас я 2 секунды делаю заставку, и тогда можно начинать трансляцию.
А мы и так уже там в YouTube.
Ну хорошо, да, просто начало. Для начала сейчас я 1 секундочку. Сейчас я включу, буквально полсекунды. Так, заставка. Опять. Сейчас. Все, давайте начинать.
Okay. Hello, everybody. I will share my screen. Just a moment. Yes, now I share my screen. I hope you can see it. And today we're really happy to see you in our roundtable, which is called Inhomogeneous Irrationality: How the Brain Makes Decisions. And I will use a few minutes, let's say 3 minutes of your time, to introduce the event and explain the event. So we are in the major conference of the High School of Economics, so-called April International Academic Conference in Economic and Social Development. And nowadays, this university is not only the School of Economics, but also has developed new faculties like Faculty of Biology, Faculty of Chemistry, and recently opened a new research institute on cognitive neuroscience. So we're really happy today to introduce our speakers. We will tell a bit more about our keynote speakers today, about Dr. Kingston Mann from University of South California and Professor Stefano Polimenteri from École Normale in Paris. I will introduce our distinguished speakers a bit later, and I would like to explain you the reasons why in the School of Economics we're talking about the brains. And today the event is organized by the new national initiative. So we here in this university, together with our partners, develop a new research center for human capital. This is a multidisciplinary research center, and this is a part of the national program to build world-class research centers. And in this consortium, there are 4 key universities, and the plan is to attract around 500 leading researchers by year 2025 in this research team. And we have different focuses in this research center, and we have a large international agenda, so we would like to increase the share of international researchers in the center to 10% in 4 years. We'd like to establish international collaboration with leading international universities and build relationship with research organizations and build some new international summer schools and make some placements and provide some internships abroad for our research staff. And today we're talking about the decision making, and I will have to explain that 2 years ago this school created an institute for cognitive neuroscience. So we started this studies on cognitive neuroscience almost 8 years ago, and we managed to make an advanced research center with multi-channel EEG, MEG, transcranial magnetic stimulation facilities, and also recently we opened a functional near-infrared spectroscopy laboratory. So we more or less have everything to study brain functions. But one of the focus on this university is decision making. So during last years, we started to publish a lot. You see that the project started in 2013, and now we're the leading Russian research center in cognitive neuroscience. And I think the quality of our papers is also improving. So this year you will see some papers in human brain imaging, in stroke, in neuroimage, scientific reports, and so on and so on. The quality of research is also growing here in this university. So we opened in the middle of May a new research center for cognitive neuroscience. And one of the key topics in our research center is decision making. So we conduct our studies in partnership with few laboratories in this university. I have to mention the laboratory, International Laboratory for Experimental and Behavioral Economics, headed by Alexis Belyanin and by Professor Heike Henning-Schmidt. And I think we have a fantastic opportunity here in this university to study decision making. I like very much this title from the journal Economist, Do Economists Need Brains? And it simply emphasizes the interest of economists in economics and in decision making. So neuroscience can provide new insights. How do we make decisions? Neuroscience provide a lot of insights for new developments in computer science. As we will see today, artificial intelligence nowadays is very much affected by ideas from cognitive neuroscience. So in neuroscience, we believe that evolution of the human brain can provide a lot of interesting insights in decision making, in the mechanism of decision making. And perhaps through evolution, our brain was shaped by various factors, evolutionary factors, to make certain decisions and perhaps sometimes to make irrational decisions. We of course understand that if we are talking about decision making, our decisions are affected by various factors, from genes to neurons, by our cognition, by our society, by global evolutionary factors. And traditionally, these factors have been studied by various disciplines, from genetics to cognitive psychology and economics. And nowadays, there is an idea that we can build a new theory, a new economic theory of decision making that can integrate these levels together. And neuroeconomics or neuroscience of decision making perhaps can provide some interesting insights into decision making. And today we make an attempt to make a look into our irrational decisions and into our emotions. And our speakers will provide some insights. How can we use our recent findings in in artificial neural networks, and how can we study distortions in our decisions using some modern experimental paradigm. So now I give this chair to Boris to introduce our speakers.
Okay. Thank you, Vasily. So I'm Boris Gutkin, and I'm one of the leading researchers at the Institute for Cognitive Neuroscience at the HSC. And it befalls to me to have the great pleasure to introduce our two speakers, who I think one can say are two rising stars in studying the role of human cognition in decision making, and particularly the role of individual differences in the sort of the human particularities of how decisions are made. So our first speaker is Dr. Kingston Mann, who is a senior research associate at the University of Southern California. He received his PhD from University of Southern California under the direction of Antonio Damasio. And over the years, his, and forgive me, Kingston, if I might malign a little bit your research topic, but he has studied on how the human brain weaves together different threads of our observations and our thoughts into a coherent perception of the world and coherent perception of self, and generates what humans are, in a sense, right? And particularly his worked on ideas that lead to formation of concepts, and his recent work has turned towards a even more futuristic direction, I think, and particularly looking at the concept and development of so-called soft robotics, of soft robots. So artificial agents, if we want, right, that have a perception of themselves and have a perception of their own vulnerabilities. And I believe that the hypothesis there is that it's precisely these vulnerabilities that lead to their strengths, just as in humans. And so today, Kingston is going to tell us about truth or consequence. And this talk about truth of consequence will be followed by presentation by my good colleague, Stefano Palminteri from École Normale Supérieure. So Stefano is a leading research scientist at the French National Health Institute, INSERM, and also he is the head of the human reinforcement learning team at the Laboratory for Cognitive and Computational Neuroscience at Superior in Paris, who I'm also part of. All right, and I think it's true to say that Stefano is one of the rising leaders in the field of human reinforcement learning and cognitive neuroscience, and also in human neuroeconomics, right? And particularly his interests over the years, after his early work where he studied decision-making in primates, he turned towards humans. And I think his work has focused on trying to understand the neural and computational basis for the limits of rationality that we see in humans, and particularly the individual basis for the kinds of biases that you see in human decision making, and how that structures our behavior in multiple contexts. And so today he will tell us about how the context in which we are embedded as individuals may in fact malign and structure and form what we remember about the value of choices that we've made before. And so without further ado, I will turn the podium over to Kingston.
And the minor remark, so we can ask questions at the end of each talk. So since we have a problem with the chat in MS Teams, please raise your hand. We will give you an opportunity to ask a question at the end of the talk. You can also use YouTube. I see 20 people watching us on YouTube. So you can simply write your question in the chat and we will transfer it to our speakers. So Kingston, we give you the chair.
All right, thank you so much. Thank you, Boris, for that very generous introduction. And I really look forward to this. I will share my slides. Are my slides visible? Okay, thank you. Okay, yeah, so once again, I'm Kingston Mann. I'm now a research assistant professor of psychology at the Brain and Creativity Institute, and that's at the University of Southern California. I'm so glad to be here and have the chance to tell you about our work. Now, the title of this talk is Truth or Consequences: Homeostatic Self-Regulation in Artificial Neural Networks. Here we'll explore the question of what happens when machines can be set up to care about the information that they are processing, just like humans do. So I am a cognitive neuroscientist, and over time, I've become more interested in importing principles of biological intelligence into artificial intelligence. We'll get into a little of that today. So in the first part of my talk, I'll first briefly review my theoretical paper with Antonio Damasio. This was published in 2019 in Nature Machine Intelligence. There we ask the question, how do feelings arise in nature? We can try to make progress in understanding natural feeling by building synthetic models of the phenomenon in machines. We will look more closely at each of these terms in the title of the paper: homeostasis, soft robotics, and feeling. So it's now the year 2021. You know, where is my robotic butler already? Put differently, why are robots still so dumb in the decisions that they make? Certainly, today's cutting-edge robots can do some neat things, but there's still a huge gulf between the specialist abilities and the grand vision of general-purpose robots. What's the source of this disconnect between our aspirations and our reality? Our group's study of the natural, as opposed to artificial, basis of intelligence has led us to identify a possible gap in current approaches to robotics. In particular, we draw on a set of theoretical contributions that my co-author Antonio Damasio has made to the understanding of biological systems endowed with feelings. He has provided a rationale for the emergence of feelings from the physiology of life regulation. So feelings are intrinsically about something. They make it possible for an organism to gravitate towards states of optimal life regulation, thus maintaining life and extending it into the future. How does the organism do this? Homeostasis describes the set of activities that living organisms undertake to maintain the physical conditions of their bodies within the narrow range needed for integrity and viability. So, quoting Walter Cannon, a pioneer of this concept, somehow the unstable stuff of which we are composed has learned the trick of maintaining stability. Shockingly to us, no machines today implement the fundamental principles of homeostasis, although there have been a few suggestive attempts. We believe this shortcoming may be responsible for the huge gap between our aspirations and the still quite pathetic reality. So there have been some attempts to build emotions into robots over the years. In living organisms, however, emotional behaviors are caused by events that carry important consequences for their well-being. These emotive robots imitate the behaviors, but without the consequences. So they are not driven by self-concern or self-regulation. They're more like puppets pulled by strings of computer code in this case. Now, our approach to building machines with something akin to feeling derives from a rich history. So on the left, Gray Walter's tortoises are illustrated with their simple sensors and effectors, and they can display interesting behaviors. More recently, on the right, the Cyber Rodent project evolved neural networks to support mating and foraging-like behaviors. But homeostatic features, if present at all, have been implemented from the outside in. Agents are instructed to maximize or keep within a set range arbitrary values. It's unappreciated by the robot itself that if these values veer to an extreme, then its own existence is jeopardized. So really, the emotions and values underlying these behaviors are not directly relevant to the system itself. All robots of this class would thus be described by the philosopher Hans Jonas as biologically indifferent. So we point to two emerging technologies that might allow us to build a new class of homeostatic machines. One, soft robotics, and two, deep neural networks for multi-sensory integration. So first, why soft robotics? The majority of today's robots are constructed from materials of convenience. So consider the life of the boxy robot on the left. In general, this sheet metal is so durable that its integrity can be safely assumed or ignored in normal usage. But this durability comes at a cost. An invulnerable material has nothing to say about its own well-being. Now, soft robots, on the other hand, more readily enter into a graceful and sensitive coupling with their environment. There are more and more interesting things that can go wrong with soft materials. So their softness holds a deep well of vulnerability for us to draw upon. Now, the past decade has witnessed the birth of soft materials and soft electronics, which can be embedded on flexible and stretchable substrates. The most recent types can even sense and localize damage to their own structures, seen in the bottom right, and they can self-repair under certain conditions. One implementation uses droplets of liquid metal suspended in a polymer. When the polymer ruptures, the metal droplets fuse and create a conducting surface, indicating the extent of one's own damage. Now, the end game, of course, is something like the miraculous material known as biological skin. Consider how densely embedded with multiple varieties of receptors and effectors our skin is. They're composed of cells that keep themselves alive, but they also register itch, pain, temperature, stretch, vibration, pressure, and it goes on. So we rely on the skin for the critical function of keeping our insides on the inside. It's our boundary against the world, and yet it's still exquisitely vulnerable to the world, such that a tiny ant's jaws can pierce it. I encourage you to check out our paper, where there's much more detail on the ethical questions and connection to reinforcement learning. But for now, I'd like to switch gears and tell you about our latest experiments implementing some of these principles in artificial neural networks. What if we can set them up to be vulnerable to the environment and to the objects over which they compute? So the idea here is to build a model of synaptic homeostasis. Neurons in the brain need to regulate their own excitability. Excitotoxicity can lead to cell death, and that's a real danger when you consume certain drugs. What if we import this idea into artificial neural networks that can recognize objects, but are also needy? They depend on those very objects for their continued integrity and functionality. Our simulated agents contain neural networks trained to recognize images from the MNIST dataset. Critically, following recognition of the object, the agent needs to make a decision whether to take it or leave it. That is, it can choose to ingest or reject the recognized digit. Here we add a twist to the common MNIST classification problem to make the network's decisions consequential to itself. The digits have direct effects on the nervous system of the agent, so there is no blood-brain barrier here. The digits 0 through 4 have inhibitory effects, and digits 5 through 9 have excitatory effects. You can think of the numbers as being either GABA agonists or AMPA agonists. These drugs can affect various components of the neural network, but here we'll look at one specific part, the learning rate hyperparameter, which controls how impressionable the network is to feedback. To behave adaptively, the agent has to answer a question akin to, how does this number make me feel? So we use a counterfactual decision process to answer a related question. How would my own functionality be affected by taking or leaving this object? So the agent first gives its best guess at what the object is on the left, and then decides what to do with it. It makes 2 copies of the base network shown on the right. In one simulation, the recognized digit is left alone, and you keep the current learning rate to perform a weight update on simulation A. In another simulation, the digit is ingested. If the digit was predicted to be 0 through 4, the learning rate is decreased. If it was predicted to be 5 through 9, the learning rate is increased. And then a weight update is accordingly performed on this simulation B. Now, the agent selects some digits from its memory of previously experienced digits and passes them through both simulation networks, A and B. The network that is more accurate in classifying previously seen digits will determine which action to take in the present. Suppose a decision is made to ingest the digit and to alter one's own learning rate. Now, the base level neural network executes this decision. In the backward pass on the real neural network, its learning rate has changed based on the true label of the digit and not necessarily the predicted label. This critically incentivizes the network to predict correctly, because otherwise there will be a divergence between its subjective simulation of the digit's effects and the objective effects of the digit upon itself. And now we add one final twist that we call the vicissitudes of life. As so often happens, the rules have a way of changing on you. On one day, you learn a mapping between the label 0 and these round squiggles. And then on another day, we randomly swap 2 of the mappings between labels and images. Label 0 now corresponds to these squiggles, and label 9 to these. And to top it off, the images now have opposite effects on your own learning rate. So typically in machine learning, you estimate the probability of a label y given the data x. In this more lively, non-stationary environment, the distributions of the data x are changing given the label y. This is a type of concept shift that we encounter in real-life machine learning problems. So our hunch is that homeostatic self-tuning of your own learning rate will allow greater flexibility to tune oneself in accordance to the changing circumstances. Now, here we can see that when you swap the labels once per epoch, over 20 epochs on the bottom, the validation accuracy is comparable between the 3 types of classifiers. The homeostat in red adaptively regulates its learning rate. The conventional classifier in green that is not affected by the digits and holds its learning rate constant. And then the randomly regulating classifier in blue that blindly chooses whether to take or leave the digit. Now, what if we make the task a little harder? We see the original graph on the left, and then on the right, we increase the rate of digit swapping from once per epoch to 10 times per epoch. And we see a decline in performance for the green, constant learning rate classifier. Interestingly, the blue, blindly choosing agent performs quite well as the homeostatic agent in red. Now we crank up the difficulty even more. Note the change in the y-axis scale here. So again, we put chance level on bottom now, and at 100 swaps per epoch, the red homeostat handily outperforms the green constant agent. The blue random agent, after some difficulty in the first half, comes to match that of the red homeostat. And finally, on the right, at the extreme of 500 swaps per epoch, or 1-digit swap per 100-digit exposures, all networks have a hard time of learning. The green constant agent performs just above chance. The blue random agent shows significant variability early on, but recovers quite well. And the red homeostatic agent maintains a respectable performance throughout. Here, we can see the aggregated results of 20 runs for each condition. Earlier, we showed a single run. And this is represented by a mean with shaded bars covering the standard error. Now, grouped by rates of concept shift, we see that in the conventional setting with no concept shift, the constant LR learning rate classifier in blue gives beautiful top performance. The random classifier in green goes wonky after some time, and the red homeostat maintains decent but not perfect performance. As we crank up the rates of concept shift from 0 to 1 swap per epoch to 10, 100, 500, the constant classifier in blue declines to a rather poor performance, scraping just above chance at this extremely inconstant environment of 500 swaps per epoch on the right. The green random classifier either gets a middling performance or it shows huge variance. But it is the red homeostatic classifier that maintains good performance throughout and indeed is superior at the very most extreme conditions of environmental change. Now, here is another view on the data showing the evolution of learning rates over time for the homeostatic classifier. On the left panel is the mean and standard error over 20 runs, and on the right panels are 20 individual traces grouped by rates of concept shift. We see first on the far right and in blue on the left, the learning rate automatically regulates itself to rise steeply and then level off at 500 swaps per epoch. At 100 swaps per epoch in green, the learning rate self-regulates to steadily rise and doesn't quite plateau within the first 50 epochs of training. And then at very low rates of concept shift in red and orange and pink, the homeostatic learning rate drops like a rock from the initial rate to bounce along at the minimum clipped learning rate. Now, the final result I want to show you is something pretty cool in which the rate of concept shift or the environmental change can vary over the course of training. You see this schedule of shift, and this is something I call seasonality, in which the rates of swaps can change from 0 to 500 swaps per epoch, back and forth. How does a classifier deal with this type of dynamic situation? On the right are the 20 individual runs of a conventional classifier in blue, showing very poor performance during the high shift periods between epochs 20 and 40 and 60 and 80. But it shows a very nice recovery when the situation calms down again. Now, comparing across the three types of classifiers, constant in blue, random in green, and homeostat in red, we see that the red homeostat recovers good performance most quickly when transitioning between calm periods of no swaps to stormy periods of 500 swaps per epoch. Compare this to the severe drop in performance of the blue conventional learning rate classifier. Note, however, that at the very end, the red homeostat does not recover quite as perfectly as the blue constant learning rate classifier when it calms down again. The homeostat kind of loses the plot and drops down to chance over time. And finally, to conclude, we think that there are three lessons to draw from living intelligences. The first is that physical vulnerability and a needfulness drives the feeling process in living organisms. We believe that soft robotics are a promising material substrate for models of feeling in machines. And then finally, when learning comes with consequences, we believe that exposing your own thinking machinery to the environment and to the consequences of your own decisions can improve your fluid intelligence. And now I'd like to thank you for your attention, and to Antonio and Hartmut Nevin for very helpful suggestions. I'd also like to acknowledge our sponsors, and I'm happy to take questions now.
Okay, so we will collect questions now. So as I suggested, you can raise your hand and we will give you an opportunity to ask the question. So while you're thinking about the question, I will ask a question from the YouTube. So Blair Shevlin asks, is the random agent truly random or just the constant agent with some noise term?
Thanks for that question. So the way the random agent is structured is that it's random in the sense of how it determines its self-regulation. So the homeostat always chooses the most self-advantageous simulation. So should I increase or decrease my learning rate? The homeostat will run the simulations and then choose the better performing one. The random agent skips that simulation and then just chooses that learning rate parameter change randomly.
Thank you. I see Boris has a question.
Yeah, I have a question. Maybe it's something, a bit of a challenge, and that is a question. So for the second part, you've told us how, essentially a signal classifier can be improved by taking into account the consequences of what it's actually doing and what's actually classified, right? And my challenge that I want to sort of, give you is that how would you translate these sort of results that you see in an, let's put it directly, in an economic setting, right? We are, in a economics conference, and I think it would be interesting if you were to try to tell our colleagues how they should think about your results.
Yes, thank you for that. I think there's different types of discovery, right? You can run, you can do theory, you can run experiments, collect empirical data, or you can run simulations and create your own data. And I think this is most useful for creating simulations of economic phenomena when you have self-interested agents. You can put many of them together, and you can start to create small economies or markets and study the dynamics and emergent larger scale patterns built up from fundamentally self-interested agents. Currently, you can have very simple agents that are just following, for example, flocking rules. And then you'll already observe some very interesting phenomena. But if you actually have, for example, flocks that try to maintain their own internal integrity, I think you'll see even more interesting economic-like phenomena emerge.
Thank you. Thank you.
Thanks, Boris.
I will ask a couple of questions from the audience. So one question is, so can you clarify the link between this idea of soft deuterative materials and this model? So can you clarify the link between these two ideas? That's question number one. Kingston, can you answer?
Yes, thank you. So the link here is we have a theory that you need physical integrity. Of course, in an artificial neural network, there's not much physical there. So we try to import some semblance of an integrity by the neural network's ability to track its own predictions with reality. So that is the closest we can get to what is self-integrity. Can I maintain good performance by regulating myself in accordance with reality? I grant that that is a bit of a stretch from truly soft, stretchable, severable materials that we would want to build and are in the process of building real robots, physical robots. And there is definitely a reality gap for artificial neural networks and soft robotics. But I think this is a good first stab at vulnerability.
Okay, thank you so much. Other questions? Because I see one question in the chat. There is a question also which asks to still link the idea of this adaptive learning and prediction of the reality and the concept of homeostasis. Is it one-to-one match, or your concept simply mimics a part of homeostasis, not the whole concept? Because I think some people have a problem to truly map your model to homeostasis in life organisms. Can you comment on this? So is it one-to-one match to the concept of homeostasis, or just a part of this idea? You inherit, use only part of this idea, yeah.
Yes, it is only the most elementary unit of homeostasis that is implemented into this artificial neural network model. As you saw, that enormous reaction cycles data that we have mapped out, maybe we capture a tiny little square in here. Again, the artificial neural network's only concern is to choose its own single learning rate parameter in order to converge its predictions with reality. And that is just a very elementary piece of homeostasis modeled here.
And perhaps the last question I see in the chats, it's more general. It's related to Antonio Damasio's ideas about some consciousness, emotional feelings. So do you think that for artificial intelligence, there is a natural limit to implement effective mechanism because of the lack of feelings, lack of conscious emotional experience? So what is your futuristic view on these issues? Would we be able to build an emotional computer, or still there are some limits related to the hardware or software as compared to organisms, living organisms?
Yeah, that's a very deep question. Are there material specific limits or requirements for true or lifelike intelligence, we can say? I've spoken at length with Antonio about this, and I think we both believe that intelligence is kind of a byproduct of life, that life always has to come first in order for intelligence to have any meaning at all. So intelligence serves life maintenance and not the other way around. If that is truly the case, and you want general, let's say, adaptive intelligence of the sort that we say we want when we want AGI, I think you need to have more lifelike properties in the physical instantiation than present currently. Currently, they're all in silico. They're completely abstracted. They're insulated from the consequences of their own actions. There's nothing it is like because nothing can go wrong for a neural network or for a robot right now. So I do believe that you need some of the life principles, if not necessarily biological materials. I think we can make convincing models with synthetic but soft and vulnerable materials.
Thanks a lot. I think, Boris, that we have to stop here our discussion. We can come back to it at the end of the roundtable, and perhaps we can switch to Stefano's presentation.
Yes.
And, Kingston, thank you so much. I hope we can come back to some questions at the end of the roundtable. Stefano, please take the stage.
Yeah, so can you hear me?
Yes.
Okay, can you see my screen?
Yes.
Perfect. Okay. So I wanted, first of all, say a few words to thank the organizer for the event. But also, I want to mention that I'm very happy to have had in the past, and I hope also in the present and in the future, continue to have some interaction with the Center of Cognitive Neuroscience and Neuroeconomics at the Higher School of Economics. So I have already collaborated in several projects with Vasily and Anna, which are very successful in terms of the results that we get. I will not be talking today about that, but I can confirm that it's a very vibrant and pleasant work environment. Okay, so today I will talk about context-dependent distorted memories of values. I Google translated the title in Russia, so better than nothing, I would say. But anyway, so let's move to the first slide. First of all, I want to point to a couple of published papers on this topic, which has been published in 2018, and one it's very fresh, or I should say hot from the oven, just published last week, which addressed the idea of context-dependent preferences in reinforcement learning. And I want also to acknowledge the two main investigators of the present project, the data that I will show today, and especially Magdalena Sukopova, but also Basil, who is helping us out. All right, so a little bit of background. Context-dependent valuation in perception, in judgment, is something that it's very well established. I will just mention a couple of major authors in this topic. For example, we have Henry Helson with the adaptation level theory. So the idea that judgments depends on the average value of the similar stimuli in a given context. He started by study perception and then applied the same principles also to other cognitive function. Similar, we have Alan Parducci with what is called the range frequency theory. So the idea that, again, the evaluation of size of stimuli, temperature, weight, but also happiness of one person depends on how an event or a stimulus map into the range of the possible stimuli. And the general popular idea is that, as you can see very well in the circle illusion, is that the perception of something is very strongly affected by its background, its context, its surroundings. These ideas from perception are not new into the neuroscience and behavioral economics literature. And in general, there is this probably one of the most important questions in behavioral economics pertaining on which behavioral models we should use. It's, does the brain calculate values? And the alternative of calculating, and I think the title here actually means, does the brain calculate absolute value or objective values? And there are a lot of alternative models, including the more prominent prospect theory model that assume that actually there is some sort of context dependence or framing effect. There is also strong evidence of context dependence in the neural correlates of economic value, and you can find it in humans with fMRI, but a couple of examples that I'm putting here in the slide comes from electrophysiology in monkeys, especially from Paul Glimcher or Padua-Schioppa results showing that some sort of outcome context dependence or normalization or value normalization apply also to neural signals that encodes values. So giving this background, as also Boris very nicely mentioned in the introduction, one of the main questions that I've been investigating in my team is that what about the same ideas before showing the behavioral paradigm that I use to actually address these questions. Let me recapitulate very quickly the reinforcement learning framework and formalism, okay? the variables are the same variables in a standard Markov decision process. So there are states, action, and rewards. The goal of the agent is to maximize rewards, and a very simplified scenario. Typically, what happens is that the subjects or the agent choose which option to choose, for example, among two possible options with a logistic or sigmoid function, so that the probability of choosing A depends on the difference in value between A and B. After making a choice, the subjects obtain a reward and can calculate a prediction error, which is essentially a surprise term, which is an error term that is used to correct expectation through a learning rate in the subsequent trial. Okay, so I should mention as a difference from what Kingston presented, my modeling is at the more algorithmic level. It's not a more implementational level as neural networks, etc. The core idea is, okay, so this is the established framework, but what about reward and punishment representations essentially in the brain of the subject? So there is some context. Is there any context dependent, any rescaling? So this is the experimental conditions that we used to investigate this process. And I will, not knowing this familiarity with the audience with this notion of reinforcement learning task, I will explain even a little bit more in detail later. So the idea is there are different learning contexts which different properties. In each case is a two-armed bandit task. So the subject has to figure out by trial and error which is the most advantageous option. And here, for example, you are in a big gain context, AB. I hope you can see my arrow, but anyway, the AB context. So there are two options that are associated with high reward, I mean, relatively high reward, €1, with different probability. And you can have a small gain context. So there is a manipulation of magnitude of the outcome. And you can have the same in the loss domain. So here, the goal of the subject in the small loss and the big loss is to actually minimize losses. Okay, it's damage limitation. Subjects do this task a lot of time with feedback. And then we have a post-learning assessment in which we essentially ask preferences among all possible options without any feedback to actually assess the learned value of the options during the learning phase. Okay. So more concretely, here what you can see is a typical trial of the learning task. There is a fixation, then the options are presented, the subject pick one of the options, receive a reward, etc. And it loop again, the subject loops again across the condition. And on the right, you have also representation of the 2x2 factorial design with valence, reward and punishment, and magnitude manipulation. And then we have the transfer test in which the subject is presented with choice without feedback. And the transfer test, there are all possible combinations. So for example, this one, which is the most advantageous one, can be compared to this option, and all possible options, okay? Now, choice preferences in the transfer test is a measure of the value of the options, right? These are the results. So first of all, I really quickly remind the intuitive prediction of, for example, of an absolute learning model should predict option values like monotonically decreasing when you go from this big gain to the big loss context, while a relative or context-dependent model should predict a pattern that is more like this, like a zigzag, because essentially this model encodes only whether or not an option is better in a given context. And these are the results, okay? So these are empirical results in the previously published paper in 2018. It's not already the new data set. And you can see that, for example, rationally, the more chosen option is this one, which is associated with €1 and 75%. And the least chosen option is this one. Okay, so this is nice. But then you can also see there is this sort of zigzag pattern that indicates some paradoxical value encoding, such as, for example, this option, this lead 10 cents with 75%, the third option, is preferred compared to this option that leads to €1 at 25%. Even more strikingly, maybe, there is also a value inversion, if I may say, between the smallest positive option and this one, which has actually a negative option value, right? So the pattern is consistent essentially with an hybrid scenario in which the options are neither completely absolutely encoded, neither completely relative encoded, okay? And yeah, the conclusion for this part is that indeed subject preferences elicited through this explicit choice are consistent with this hybrid scheme, okay? Now, let's go to the research question of the current project, okay? The general question is, do explicit memory representations present the same distortions, which can actually separate into different related questions? So is this pattern robust across different elicitation methods? And I will see what I mean. And the other question is this pattern robust when essentially we employ different decision-making modalities, okay? So essentially the idea is that what we show in the first study is that when we elicit preferences with a choice, maybe we tap into procedural memory and we have context-dependent values. But it could be the case that if you use other form of elicitation, which are more episodic or stimulus-bound, then we elicit another memory system, for example, more explicit and declarative, and we could elicit absolute value, thus showing that the effect that I showed you before is not universal. The other question is that I show this effect for choice between options in bandits in what is called reinforcement learning or experience-based decision. But what about choice among lotteries or memories of choice among lotteries? That is a more standard paradigm used in behavioral economics, okay? So this is the experimental protocol. We run a lot of experiments online, but they were fully incentivized, so people were paid as a function of the actual reward. And they started all with, of course, instruction training, followed by the learning phase, in which the subject acquired the values, and then two elicitation phase, one, the standard choice preferences, and the other one, another elicitation that I will describe later, which tap into explicit memory or more declarative memory. We also run the same experiment in a second day. I will not present these results today, but spoiler alert, they confirm all the results that we know from the day one. This is the design. It's just the same as before, big loss, small loss, etc. We just changed the euros into points that had a specific economic value. And the layout was a little bit different. Also a difference is that in this case, we were systematically in a complete feedback situation. So the subject was informed about the chosen outcome, but also the foregone option, okay? Just to be sure that there was no limitation in the information sampling. So the subject has as much information as possible to avoid sampling bias, partial information, ambiguity, etc. So these are the results of the online experiment. It's essentially the same results as before in the choice-based elicitation. And I will first describe the results for the worst possible option and the best possible option. So you can see that there is a very huge difference in choice preferences, signifying that people is significantly learning the value. In this representation, the size of the circles represents how many subjects there are for a given value, right? And the X represented the median value, and the dot is the average as usual. Now let's see what happens in the other condition. Already here, you can see that we replicate the context-dependent preferences because the minus 22, this is the expected value of the symbol. The minus 22 symbols is preferred compared to the minus 7, and actually even slightly positively evaluated, okay, above 50%. Move forward, we again have the same effect. So you can see here, for example, the plus 2.5 symbol is less preferred compared to the minus 2 and the which is not rational, of course. And again, you can see that finally the plus 22 is essentially chosen very few times, much less compared to the expected value 7 symbols, etc., etc. So essentially, we fully replicate online the pattern that we observed in the previous study in the lab. Now, let's move to the interesting part. So this is the replication, okay? So choice-based elicitation, we found context-dependent irrational preferences. In another experiment, we asked, in the other form of elicitation, we asked, okay, so this is the symbol. Tell me, what was the most frequent outcome for this symbol, okay? We show the results. We just rank transformed the results so that they are bounded between 0 and 1. Well, these are the results. So again, you can see that there is a strong zigzag pattern, which is consistent with context-dependent value retrieval, also for explicit values. So this is one formal visitation. And here you have the triangles indicate what will be the correct response in this task. Because for some options, for example, 0 is the correct response, right? We thought that this maybe was a limitation of this test, and we ran an additional experiment in which this time, instead of just having a forced choice between 5 possible outcomes, we asked it on a Likert scale from -100 to +100. Okay, try to retrieve what was the expected value of the option. And again, these tests were incentivized. And these are the results that we observed. So even when we elicit the values on an absolute scale, we find the same violation of monotonicity, because now you can see the normative or rational response here, the triangles should be a strictly monotonic function, okay, with the best on the top and the worst on the bottom. And instead of that, we replicate that even explicitly people provide this value that are consistent with the value context dependence value. And finally, we wanted a third confirmation to avoid all possible confound. We separately asked it first to tell us what was the non-zero outcome for a given Q, and second to tell us what was the probability of this non-zero outcome for this Q. Again, we find the same pattern. Okay, so even with this very explicit and very complete assessment of the memory of the value of the outcome, we found the deviation. So you now know the pattern is the fact that you can find essentially these options prefer to this one, the -22 prefers to the -7, the -2 prefers to the -2, to the +2, sorry, etc., etc. So the interim conclusions are, we really confirm that if options are presented in stable decision context, their economic value is learned in a context-dependent manner. And these results are robust and replicable online in the lab and across different elicitation methods, thus suggesting that essentially even more declarative and explicit memory systems present the same representations as other memory systems that are maybe involved in more procedural or choice-based retrieval. In the second part of this study, we want to assess whether we can actually manipulate preferences by manipulating the learning context, right? So here, this is the standard task. In another task, what we created new fixed pairs. Essentially, we moved this option here, here, and vice versa. And we did the same here. So now, essentially, before the task was a comparison between different probability, but with the same magnitude. Here, the task is a comparison between same probability, but different magnitudes, okay? So we want to see whether, and finally, so in a third experiment, we have also the learning test presenting all possible combinations, okay? So these experiments are crucial because if the previous results are induced by some fixed property of the outcomes, by modifying the learning context, I should not modify the preferences. So this is the result that they obtain. In the fixed pair case, we replicate once again the pattern that we know. And what happens when we change the learning context? Well, we change also the preferences. So you can already see that the pattern is not the same. And in a second, I will highlight some specific preferences. And here in the situation in which there is a training with all possible combination, and finally in this case, and only in this case, we can retrieve a rational monotonic increase. So let's focus on these 3 Qs, for example. So you can see that, so again, let me remind that in terms of informational content, the 3 tasks are the same because the feedback is full and the subject experience all trial and all options the same amount of time. So they receive a stream of information in terms of outcomes that is exactly the same, yet the shape of the learning context drastically modify the shape of the subjective value associated to these options, okay? And we understand this process to a point that we know how to modify the learning cortex in order to shape essentially the values that whatever value scheme we want at the end. So the interim conclusion test, by manipulating the decision context in the learning task, we can influence the subsequent preferences. And this is kind of a nightmare for economics, right? Because it shows that this very same value, the very same stream of information results to different preferences at the end. The third question was to see whether it generalized to value in memory that are originated by a different process. And you know, in neuroeconomics, we have two major paradigms. The standard paradigm that comes from the animal learning literature for artificial intelligence is experience-based choice, reinforcement learning. And then there is the paradigms that come from the behavioral economics, Kahneman and Tversky, etc., which is choice among different lotteries, okay? It is interesting to compare these two decision modalities because we know that they elicit very different decision-making process, right? So for example, there is something in the literature that is called the experience description gap that says that, for example, probability distortion, value function, the fundamental characteristics of the decision theory parameters are not the same whether value is vehiculated through lotteries or learned by experience, okay? To assess whether or not these biases are applied to this kind of choice, we run, so we already have the experience-based paradigm. We modify the paradigm into a version that is description-based, so no outcome at the end, but explicit information later, and subject were nonetheless told to associate the symbol to the lottery because they will be asked the question later. And we have also a hybrid scenario, okay? So with a choice and then a choice confirmation, followed by not an outcome, but an explicit information about the value of the stimuli, okay? So these are the preferences in the experience-based paradigm, same as before, zigzag pattern that corresponds to context-dependent preferences. Let's see what happens in the hybrid scenario. Again, the pattern is preserved. And finally, also, even if it is noisier in this case, because probably subjects are not very facilitating to associate the essential information to the lottery because all the information is complete, yet as much as information we can retrieve from this description-based paradigm, you can see that it also comply with the notion of context dependency. So yeah, so this is the result. So again, full information, yet distorted memories of this value. So to wrap up, these are the final conclusions. So first, I will remind, if options are presented in stable decision context, their economic values learned in a context-dependent manner, which shows essentially the universality of the principle of context dependency also to first reinforcement learning, and second to options that are actually stored in memory, so value that are actually stored in memory. Second, the results are robust and replicable across different elicitation methods, which are supposed to tap into different memory systems. So there is only one representation, apparently, at least as far as we are able to tell across 4 elicitation methods. We manipulate the decision context and or the learning context, and we manipulate the subsequent preferences and the value estimate. And you can see how this paradigm has, conceptual importance for all, for example, debate about choice architecture, learning architecture. So you change the learning, you change the value and the preferences. And finally, these results are kind of universal across decision modes. So they exist both in the experience-based and description-based. So 2 reasons why I think these results are great as compared to those other things is that, often one problem in behavioral economics is quite the contrary, is the idea that the construction of preferences paradigm dictates that essentially the way in which you elicit the preferences, you will retrieve different preferences. Here we are in instance of the opposite. So regardless of the way in which you elicit preferences, you find the same bias, namely context dependence. Second, the standard result in behavioral economics is there is a gap, there are differences between experience and description. And again, we find an instance in which is not the case. So our bias, our memory bias, are both present in experience and description. And I think this is important if in behavioral economics, thanks to inputs from neuroscience, from perception, etc., we move from a collection of anomalies, of principle, of specific effects with specific case, etc., scenarios, to more the search for general and universal process. Second, I wanted to just to put, maybe to connect later in the discussion on the question about the question of rationality and also the question of homeostasis. The idea that there are, first of all, this bias is also found in animals. So they seems to be hardwired and quite preserved across evolution. And second, we could also debate, and we are also investigating in the lab through simulation, what could be the rationality of these learning biases. And finally, I wanted to conclude like with maybe a visual, like a very concrete example of what we are talking about and why I think that these results are striking. Okay, so now it's gonna take just a few seconds. I will play the task for one of the subject that was experiencing this in this big loss scenario. Okay, so you will see all the choice. Sorry, it started not at 0, but you know there are 24 tries. So you can see this is the stream of information. Okay, so a subject was playing this task, for example, choosing the pink one and having 0, 90 sometimes, etc., etc. And later, this very same subject is asked what was the value of the pink, and he replied or she replied 10 4 times. So you can see that how striking is this effect, right? So this is, for me, one of the most striking behavioral biases that, at least in my career, I was able to demonstrate. This being said, I wanted to thanks again general my team for many interesting discussion about this topic, but specifically Magdalena, which is the first author of this study, and Basil, who is also implicated, and also Sophie, which was first author of the first 2 studies of this line of research. And thank you very much again to you for your attention and the organizers.
Thank you so much. So now we can collect questions. I will ask a question from the audience, from the YouTube. I think you partly answered some of this question, but still. Blair Shivlin asks, did the same subjects who gave rating also make choices? If so, for those who gave accurate rating estimates, did their choices also show context-dependent irrational preferences?
So first of all, yes. So there were for each subject there were always at least 2 elicitation methods: one choice-based preferences, and the other one that was memory-related. Okay. So now 2 things is the relation between accuracy between different elicitations. So first of all, there is a significant correlation between the context-dependent bias across elicitation methods. So for example, we try to quantify, actually we quantify to different models the zigzagness of the pattern, and the same measure tested in the choice-based preferences or in the episodic memory preferences is correlated. Second possibility of the question is also correlation between the accuracy during the learning phase and the, in general, elicitation phase. And this is a paradoxical result that is analyzed in depth in the Science Advanced paper in 2021, the very recent one. There is a paradoxical relation. So the better the subject is in the learning phase, the bigger is value deformation in the transfer phase. So highlighting this idea that there is a trade-off for rationality here, right? So it's to be very good in one context that you lose in extrapolation power. Sorry, Vasily, you are mute. Or I can't hear.
Ksenia has a question. I will switch on the microphone. Ksenia, feel free to ask the question.
Yes, thank you. And thank you for a very nice talk. And I had a question. Well, actually, if I understand correctly, there are 2 things that people learn. One is the value of the I mean, the gain or loss, right? The size of the amount of money, for example, they win or lose. And second is the frequency with which it happens, right? So can it be that actually the problem is not in the way the values are learned, but actually the frequency is my perception of frequency depends on the context? Could it be, or is it?
Yes. First of all, let me clarify that in the elicitation memory test, in which we asked separately the points and the probability, the results that they gave is the post hoc calculation of the expected value of the symbols based on the value of the subject. Okay. First clarification. Second point, if we look only at probability estimations, people are quite bad on that. There is some signal, so there is a strong regression to the mean, regression to 50%, first problem. And second, the two extreme options are quite well remembered, like the best and the worst. And there's others, there is a little signal, but they are not very good at that. I don't know if there is some intrinsic the probability learning separate from value. Probably we should have a more better like elicitation of the probability or more clear asking these questions. But this is, of course, the only experiment in which they are very good at estimating the probability is when the probability was written at the moment of the outcome. Because like it was written, even in that case, they were not perfect.
And also, if I'm allowed by the chair, also a second question. So basically, when they have to make a choice, which symbol they prefer, it's the same as basically I have to choose between two different lotteries, right? Although these lotteries are just their perception instead of actual lottery that they would see. And so this means that there are, well, two things that are important, which is the mean, the expected value, but also the variance, right? So could it also be that these patterns that we see are not necessarily due to the mean calculations, but rather because they have a distorted perception of variances?
So the objective variance is the same, right? Because in the two options we have 75-20% and 25%. I don't think so for two reasons. So essentially, one of the whole point of manipulating the learning context is that every interpretation that relies on the fact that there is some intrinsic property of an outcome, for example, minus 90.25%, should predict that you do not shape, you do not change the preferences if you modify the arrangement, right? So what showed the experiment in which we modify the learning context is that you keep the same variance, you keep the same expected value, you put the very same thing in a different context, and then in the memory of the subject, there is a different representation. Mm-hmm. This is so classical criticism rejected by model comparison, but that we get, for example, some effects could be explained by what if they are encoding the utility and not the, no, because I shift the context and I obtain a different result. Or what if they were using an additive model in which they were summing up the magnitude and the probability? Again, no, because I changed the shape, you know. Mm-hmm, and I think I never thought about the variance perception problem, but for me, the variance perception interpretation falls within the category that are interpretation based on the quality of the outcome. And all these interpretations are rejected by the fact that when I change the learning context, I change the preference, one. And second, in case in which I give a feedback in the transfer test, they do revise their preferences when they are capable to extract a new contextual information. And again, this is in the 2021 paper.
Mm-hmm. Thank you.
Okay, other questions? There are a couple of questions in the audience. They're quite general. So first question is, can you speculate a bit, Stefano, about the reasons for such context dependence effects? I mean, what are biological reasons? Yeah.
Yes, there are. So there are. We should. So I think there are two essentially possible routes, which are not necessarily mutually exclusive. Okay. Of course, as everybody in the audience, I believe in evolution, and I think that every cognitive process is responding to an adaptive fitness question. Okay, so essentially maximize the gain of the system minus the constraints, the cost that you can have. Two things. So the high-level interpretation is that this context dependence may be ecologically rational, okay? So for example, you can see that if you are in an environment or in a season in which there are a lot of resources versus a season in which there is not much food, you better have a boost of memory for the outcomes that are rare because they are in a very bad context, because it's what really matters, okay? So this is one kind of interpretation. And for example, in the paper that I showed you by McNamara, which is essentially an evolutionary psychologist, they investigated the reason and the conditions under which this state-dependent valuation, that in their case is more internal state also when I'm hungry versus when I'm not hungry, linking to homeostasis. The second interpretation is microscopic. So value, and it comes from also perceptual and decision science. Values or whatever variable is encoded in a brain, and a brain is a machine that is encoding information with firing rates, neurons that have very strong physically constraints. They are energetically caustic. They don't have a negative firing rates, and they have a response function that is bounded, okay? So we already know in perception that essentially adaptation level, or the brain, what it does is that it adjusts the tuning function to the distribution of the stimuli in order to obtain the maximum discriminability for the distribution of the stimuli. So you will make in your life a decision for which snack you want to buy, or which apartment you want to buy, or if you are Jeff Bezos, which island you want to buy. You cannot imagine, I mean, it's a caricature, that neurons are encoding linearly outcome value on such huge different scales. So the representation has to be put in a bounded value scheme, right? And this is why it is normative. So essentially, it allows you to adjust the gain function. You pay the increase on discriminability by creating memories that do not reflect reality. And this, I think, really interesting. We should think more about this, I guess. But there can be at least this both neurobiologically normative and ecologically normative interpretation to this effect.
Mm-hmm. Thank you so much. I think another question from the audience is related to your last comment. So the question is whether you think in the brain we can find very different valuation signals. Could you speculate whether there are brain areas where activity is context dependent, but perhaps still there are some brain areas which are not affected by context? Similar to some, I would add, perhaps it's similar to some other studies, let's say with temporal discounting, showing that some brain regions are very much affected by the temporal delays of rewards, but others are not. And what do you think, Stefano?
Yeah, so first of all, if it's a good question. I have some grant in evaluation to try to address it. So I hope if the reviewer of the grant is on the audience, that he can appreciate other people share the interest for this question. The subject to the task. When some part in the brain is going to encoding -90 or 0, because this is in the visual field. So there will be at least the very peripheric representation in the absolute scale. And we already know for other studies in different tasks, or at least we strongly suspect that representation in the ventromedial prefrontal cortex is probably more in the orbitofrontal cortex, or more in the terminal state of the decision process, are strongly context dependent. I think the million-dollar question is where the transformation is made. And also for me, and this is a question that my skills cannot address, but people like Kingston and others could, what neural network can actually operate this transformation from a percept that is an absolute scale and then a representation that is completely normalized? Yeah, but I guess that in the prefrontal parts, we will find normalized representations.
Mm-hmm. Okay, and almost last question from the audience, I think. I think it's for both presenters. So since we're talking about irrationality of decision-making related to values and emotions, what would you take from this emotional mechanism to new effective technologies? What you would avoid to implement in new emotional computers? So I think the general question from the audience is, do you see some disadvantages of this natural decision-making system that we shouldn't implement into the affecting computing, or everything basically from our brain mechanisms of decision making should be translated to artificial intelligence? So I think this is a question for both.
I will maybe start because my answer is going to be quite quick, because essentially it's not really my ally thinking about artificial intelligence. I do think that, of course, prima facie, when you think about a computational process that induces a bias, you should reject is like not something that you want to have in our artificial intelligence. Yet I think that maybe the idea that we can get from our results is that we navigate an environments, and environments we actually do not know what is the range of the possible outcome in a given situation, right? And if truly at some point we want to have a very general purpose machine, so let me reframe. There are a lot of even like DeepMind, AlphaGo, whatever, all works with a reward function that is specified by the experimenter. So you tell the machine what is 1 + 1 and what is 0. But this is something very artificial. So my line of research is try to find out how a machine or actually a human being learn to identify what is a good and a bad outcome in a given situation, right? And this maybe can be stimulating, but again, I'm more in the behavioral and neural side than on the other part.
Kingston, perhaps we can also ask you this question. So,
yes.
So, what do you think? What from this irrational mechanism should be translated to these emotional networks, or perhaps you think that still some aspects of natural mechanisms of decision making are not necessary for the next further development of these technologies? So what do you think about it?
Yeah, sure. First, I'd like to just respond and say that was a fascinating work presented by Stefano. Thank you. And I think it does really highlight that there is, the so-called irrational biases. There's a level of wisdom encoded in there. Again, as Stefano mentioned, over evolution, there is a level of reasoning that maybe transcends our quite narrow rationality. It is, optimizing on this narrow definition of rationality that gets you to these reductio ad absurdum arguments that get you to these exponential thinking or robot takeover, paperclip maximizers. So there's a level of biological constraints that, when you take into account, get you much more lifelike, realistic, user-friendly intelligences. So I would resist thinking of irrationality as strictly a defect. I think it is a useful trade-off in hardcore efficiency for flexibility.
Kingston, thank you so much. I now switch to Boris. Boris, we only have a few minutes to finish our roundtable. Yeah. Do you have some questions, comments?
Yeah. Actually, I just, to follow up this discussion about the usefulness of apparent irrationality, right? Let's call it apparent irrationality, right? And the usefulness of emotionality and state dependence. Let me think about, in terms of, let's say that I have a trading bot that is trading on the Forex market, okay? All right, and I turned it on so that it could do the job for me, and I could go around making my, generally esoteric models of how the brain works, and in the background, that thing turns out, some sort of nice profit of return. Now, this machine that's working there is not emotional. It's not irrational in the sense that it's programmed to do a particular function, right? It follows indices and it sort of looks for trends, and whenever the trends turn, it does one thing or another. And if it's well programmed, it will do the right thing in the long term, and I'm going to be very happy and buy that island from Jeff Bezos, right? you know, so what's the usefulness of making that bot getting, to reflect certain aspects of human frailty, let's put it this way, what's the usefulness of it getting tired, like I do, for example, like we all do, or what's the usefulness of that bot, being infected by irrational, what is it called, the exuberant optimism or whatever it was, right? So this is a kind of a challenge, right? So because in some sense we think about artificial intelligence as something that can help us and better us. So yeah. Anyway, I'll stop babbling and let you guys.
I just want to first respond that if it's a market and you're training against other humans, it should help you to build in human type foibles and fallibility into your bot. But as is becoming, when bots are just training against bots, maybe having the overhead of emotionality would be a strict defect.
So I guess it is context dependence. It's really dependent on what context you're operating in, right? If you're really thinking about, artificial agents that are interacting with biological beings, right? Then perhaps, emulating certain kinds of non-explicit trends and differences in decision-making, like emotionality, for example, right? Or dependence on the internal states would be useful. Right. So
that actually brings me to a question I had for Stefano. Have you thought about the internal context and how that might influence what you would pay more attention to? If, for example, you go on a run of a string of losses, does that change your learning strategy? Do you think? What are your thoughts?
Kingston, this is a wonderful question. So as a matter of fact, we have already some data and some of idea of project about what define a context. So essentially in the line of research or in the stream of experiment I showed you, we used a very minimal definition. A context is a pair of what is a pair of things, what is in the immediate background, right? We already have a preliminary evidence, for example. The experiment you suggest essentially, if you cluster on time the choice context of the same nature, you even increase context dependency, which essentially show that there is a hierarchy or different layer of context. So there is the local context, which is essentially the other option that is presented together, but there is also a higher hierarchical level that is whether you're in a good phase of the task or not, and this has definitely has an influence. And the other thing that we cannot study, not easily, at least with the secondary rewards, but based on studies, for example, in animals, and I think also in humans is going to be the same, for sure, I think that in your internal bodily states can participate to the definition of the context broadly, right? So the same thing, experience in a state of angry or not, probably the value is gonna depend on the homeostatic gain that you have. And I'm sure you will not remember it in the same way. And like you have in the popular ideas that the smart cook make you wait before serving you food, right? Because it's gonna increase the hungry, and therefore you're gonna find it great. But this is gonna also affect the memory of the experience, and you have either chance in the great restaurants. Often is the case that you have a very long waiting. So yeah, context here was very broadly defined, minimally defined, but I do think that there are, it's a multifaceted context, even construct, if you want, with both external components at different layers, different, let's say, time integration scale, and also internally.
Can I? So there is a growing body of literature in animal studies that shows that indeed apparent valuation as apparent from animal behavior and as apparent from the responses of dopamine nuclei in the brain that signal, in fact, motivation and reward prediction errors are exquisitely dependent on the internal state of the animal. For example, there's beautiful work on sodium appetite that shows if the animal is not depleted in sodium, it will avoid sodium, right? So negative value, right? The minute you deplete it of sodium, it will work for sodium very hard, so positive value. Okay, so this is clear internal context dependent, switching of balance from reward to punishment and back. Yeah, and so I think it's a really fascinating question that we've actually been thinking about with Vasily and with Etienne Coquelin also, and that is, can one think about money as having some sort of an internal context dependence as well, right? So we've been trying to design a project where we manipulate sort of monetary endowment of subjects and to see whether changes in this monetary endowment coupled with changes in the scale of monetary rewards actually could lead to sort of reversals of preferences or value, changes in valuation or changes of choices, right? And we think that we're going to be able to find that, right? Which would be, to my mind, is very interesting.
I think you could have a manipulation in which you add an additional step. So essentially you create a fake currency in your experiment in which you can translate into the actual money when you reach an objective.
Yeah, that's right. That's it.
And therefore you can measure the distance to the objective as the homeostatic value of the outcome. And then you can you can have a combination of options in new situations and see whether the memory is affected by the position and the accumulation of wealth in the virtual economy.
Stefano, you've hit an idea that Vasily and his and Etienne's graduate student Anush had actually, and this also chimes into some of the ideas that Christopher Sommerfeld published recently, where his, even imaging work suggests that we don't work constantly for increase of wealth, but we tend to work to reach particular monetary goals. And once we reach them, either they remap or we change our behaviors or we change our valuation. Yeah.
Although I'd be very surprised if money actually ever became negatively valenced. I don't know when more is not better.
That depends on what that money has an impact on your life. If all of a sudden you have to protect your kids with 7 bodyguards, maybe that's going to change things, right? Or if you're taxed at 60% rate or something like this, or you have to.
There is also inequality aversion. Like people don't like to be poorer than others, but they also don't like to be richer than others.
Exactly. So that points to some kind of a stasis, right? Some sort of a balance, social allostasis, if you wish. Mm-hmm. And of course, we're all differentially sensitive to that, right?
So I have to remind you that we're 5 minutes, I think, late. So I think perhaps even discussion is fantastic and very interesting. I think we have to finish, but it's a couple of concluding remarks, and I think we have to unfortunately finish our meeting today.
Well, I think I would like to thank everybody for attending our roundtable, which I think I can rationally say has been exceptionally interesting and exciting. And I would very much like to thank our 2 speakers, so Kingston Mann, for whom it's very early in the morning, and Stefano Palmenteri, for whom it's the end of the afternoon in Paris. And I see he's at work, actually, so he escaped his kids for a couple hours, I suppose. And I also would like to thank Vasily for being the co-chairman, and of course, I'd like to thank myself for being the co-chairman also, and also the Higher School of Economics technical term for helping us to set it up, and the organizing committee to organize it. And I believe our roundtable will be available on YouTube, right? Correct me if I'm correct. So, okay, thank you very much. And
thank you again, the organizer.
Come back on Friday for Antonio Damasio's lecture. Okay.
Thank you so much. See you all, guys. Thank you so much.
Thank you.
Bye. Bye.
Thank you. Bye.